So, welcome to our weekly seminar. Today we have the pleasure of hosting Adrian Misselwitz from the Optical Institute. He's a PhD student working on this topic, and he's working on topics in QED and impurity. Today he will present the outcome on his most recent work relating to the basis of speech controls of speech. Please, Adrian, the stage is yours.
Thank you very much. Yes, okay, so as Enrico already said, today I'll be working, I'll be presenting a work that we recently put on our archive titled Strongly Interacting Phase of Spins and Bosons in Circuit QED. So because this is, I guess, a bit of a more general audience, let me motivate this sort of setup that we're working with from a very sort of big picture analysis. So one of the kind of like the standard ways for probing light matter interactions is cavity QED. Cavity QED is essentially the idea that you take two mirrors, you put them close to each other, you trap some light inside, and then you can put some matter, which in our case is then kind of abstracted as just a single two-level system, some atom. You can put this inside, and you essentially kind of can analyze and experiment with how the light interacts with the matter, how it absorbs and gets emitted by it. And this is like theory, and this work that has been done already for the past decades and is all well understood. And so one kind of natural generalization of this is to say, well, a cavity itself is essentially something like a zero-dimensional system. It's just a dot. Let's expand the system into 1D. The easiest way to do this is by saying, okay, let's instead of just take one cavity, we just take several cavities, chain them along to each other into a one-dimensional array, also known as a cavity array. And then we can add our two-level systems into these cavities and see what happens. The point here is also that if you take your cavities and kind of put them close enough together, then essentially the evanescent wave of the localized photons still has some kind of overlap with the neighboring cavities, which allows for some small hopping matrix element that allows for essentially photons that are localized in one cavity with some probability to hop to the neighboring cavities, which essentially gives you then an effective Hamiltonian of a system of particles that are localized on some site, like a lattice, that can hop between neighboring lattice sites. And this is, waveguide QED, which is going to be the kind of physical setup that I'll be talking about today. Now, experimentally, it can be quite challenging to still kind of implement these like cavity arrays because there's a lot of kind of like overhead that you have to work with. So one recent development that kind of garnered interest is the idea of saying, well, is to kind of implement these theories that we develop for these types of systems in circuit architectures instead, known as circuit QED. The idea there is basically that we say, well, if we look at our photonic modes in our cavity, I mean, this is essentially a harmonic oscillator that we have in there. And this harmonic oscillator we can also describe by simple LC circuits, right, from circuits. The two-level systems that we work here with, we can essentially describe as a anharmonic oscillator, which you can produce by taking something like a circuit, adding a Josephson junction in there, which creates a natural anharmonicity. This is exactly the process that is used by quantum computing to create the computational subspace of 0 and 1. So we see that, essentially, like we can have this mapping between the kind of physical system of this waveguide and cavity QED, and we can map essentially the theories that we use to describe these systems. We can map on circuit setups as well. And the idea is there that we say, okay, well, these circuit setups, there's a lot of work being done right now on it. There's a lot of kind of growth and scaling. There's a lot of industrial, like industries like working a lot on it because of quantum computational abilities. That this can be a good platform to essentially model and implement all the theories that we've worked so far on in the photonic case. And so this is a little bit kind of the direction that we're working in there, saying, okay, we want to take essentially the theories that have been developed and that are kind of like well understood in this purely photonic picture. If we now map them onto our circuit QED systems, on our circuit setups, we want to see, okay, what happens, what changes? And one kind of like nice property is that this mapping essentially allows us, especially as theorists, to kind of like a bit more of a degree of freedom of playing around with some properties. So for example, as I mentioned, we can map a simple cavity with an LC circuit, that's just a harmonic oscillator, but kind of like from a playing around with your elements kind of perspective, you can also say, well, let's switch out the LC circuit for a superconducting circuit, right? So some kind of structure that has a nonlinearity, right? This is sort of a very natural and simple implementation in these circuit setups. But what it effectively means is that we introduce nonlinearities into our cavities. And this is sort of essentially the approach that we have. But a nonlinearity in our energy spectrum in a local cavity effectively means that we have some sort of now particle number dependent energies that we see, which means we essentially are modeling particle interactions, which is something sort of not very straightforward, because so far, I mean, if you just look at purely photons, photons don't really interact. They don't see each other, so you're kind of like limited to non-interacting particles most of the time. In these implementations, by just adding Josephson junction elements, you all of a sudden like kind of very naturally get models and Hamiltonians where these interactions are present. And so our idea that we want to kind of like consider them is essentially exactly a waveguide QED setup. So we want to look at some kind of like long chain, couple atoms to it. So this is like typical waveguide QED. The Hamiltonian that we want to consider essentially consists of some energy term of just photons sitting in the cavity, an energy term of an excitation of the atom. We consider a nearest neighbor hopping between the cavities, so nothing long range, and a coupling between the cavities and the atoms. That, I mean, here like we're essentially using a rotating wave approximation, which for our purposes means that essentially the Hamiltonian is charge conserving. That means a single photon get emitted by the atom and can get absorbed by the atom. But the total number of charges in our system always stays conserved under any kind of dynamics that we have. And then lastly, what kind of like the twist is that we're kind of like looking at here is saying, well, in these implementations now, if we say, okay, we take this model and we implement it into circuits, we can now engineer ourselves nonlinearities into these cavities. And sort of like to the lowest order nonlinearity, you can model as a Kerr interaction. So some kind of nonlinearity that acts on my cavity sites. And so, yeah, this is essentially the model that we want to investigate. And the angle that we kind of want to approach from this is saying, well, okay, well, what is kind of one of the hallmarks of waveguide QED is the formation of bound states. What is a bound state? A bound state is essentially an eigenstate of my system that we currently see in the single particle picture. So in a single particle eigenstate, where we say, okay, if I have some coupling strength to my atom, I will find an eigenstate in my spectrum where this photon is essentially not freely delocalized in my system, but it is, you see this kind of like localization coming around the atom with some exponential decay. And the peak of this, I mean, sketched here is sort of the probability profile of this bound state. And we see it peaking around the cavity that is attached to the atom. This bound state is well understood. And so now kind of like our first question is to say, okay, well, how can these bound states, which are kind of very typical and well understood waveguide QED phenomena, if we now do this implementation on circuits, right, where we now have these interactions, how does it change? Like how much is still left? What kind of like comes different if we now have these interactions in our models? Yes, so for the single photon bound state, if you just have a single photon, a single atom, we can basically sketch the entire spectrum of our system. You essentially have states, either the photon, like so you have eigenstates essentially where the photon is really delocalized, it doesn't see the atom, this is just your typical Bloch states, and you just have a band here. Or you have exactly eigenstates where they are bounded, these are the bound states, where you can get one kind of like positive and negative bound state around this central band. This is all kind of done for single particles. For single particles, there's no interaction. This kind of like all stays the same, and this is something we understand. But now we can scale this up, say, okay, well, let's consider two particles. What changes? Just kind of like to keep everyone on the same page. Without interaction, this is again a picture that's well understood. For two particles, we essentially get a qualitatively similar picture, just with a few additions. We have again the band of this time both photons just essentially freely delocalized in the waveguide, both of them in the lowest Bloch mode, just chilling basically completely delocalized. You now have your states where one of the photons is bounded. So one of the photons is localized around the atom, and the other one is completely free in the waveguide. And then you have your kind of new states forming where both photons are bounded to the atom. So you can have multi-photon bound states to the atom. This is kind of like one of the most like important things that we'll be considering later. All right, so this kind of like is all that changes. So far, this picture is for no interactions. This is kind of purely waveguide QED, the way it's understood. Now, if we add interactions into our picture, what changes? A few things. Not every state changes. Basically, things only change if the two photons have like feel the interaction. They only feel interaction if their profile overlaps in some way. So for example, in the states where they're essentially both delocalized, they have a vanishing overlap, means there's no interaction. Same for this one as well. We have a photon that's localized, the other one is completely delocalized, no overlap, no interaction. But the states where they do have an overlap, such as our bound states, right, where both photons are localized around the atom, those have a considerable overlap. And what happens is my two bound states essentially kind of get a shift upwards in their energy, which is proportional to the interaction. And just for the completeness, we also observe kind of the formation of a new type of state, which consists of the two photons binding kind of like to each other, so as becoming sort of a pair, but not coupled to the atom. So essentially it becomes a localized pair. The two photons sit on top of each other, and together they're freely delocalized in the waveguide. This is a kind of state that's already been considered, is already like known in the literature, so that's why we're not going to be considering this kind of state. I just wanted to mention it here just for the completeness of the picture. What I do want to kind of draw your attention to, though, is that we observe in this shifting of the bound states. Essentially what we see, or what is sketched here, is that we see essentially a level crossing of our ground state. So we see that for some kind of parameters, like the ratio will be G over U, we'll see that if we look at the ground state, which later on will be motivating this kind of like going into a many-body state system, and so there we want to look at ground state properties. This is why now we want to look a little bit into the low energy to like lowest eigenenergy states. You see essentially a first-order crossing between the two-photon bound state as the lowest state and the one-photon, like one bound crossing. Right, so we see our ground state will change from both are bound to only one is bound. And this is something like depending on the kind of the ratio between U and G. And this is something we want to explore a bit further because this, has some kind of like interesting properties. Also, I think something I haven't mentioned explicitly, in general, the interactions that we have in our this nonlinearity, it can be in general positive or negative, depending on the architecture. This is also, the trans one, for example, technically has a naturally negative interaction. For our analysis, we'll be focusing mostly on, or just purely on repulsive interactions. We have also looked at attractive interactions, but I'll say kind of like spoiler, like there's not that much interesting new physics coming out of attractive interactions. Also, there's a problem that if you scale the system then later on up to many, many particles, attractive interactions becomes a problem because then the ground state will be everybody bunched up together because it's energetically preferable because of attractive interactions. And this then leads to an unstable state, which in the thermodynamic limit just becomes unphysical. So this is something that you kind of have to be aware of. And because we anyways don't see that much interesting physics, we're here just focusing or just kind of restricting ourselves to just repulsive interactions, which anyways, get like the nicer physics. Right, so we wanted to understand a little bit better these transitions between the lowest eigenstates. And so one way to do this is say, okay, well, in general, many photon bound states difficult. But we can kind of like restrict ourselves to kind of a simple setup, which is the James-Cummings limit. Essentially, James-Cummings limit means the hopping that we have inside our waveguide, we set that to 0. So our J hopping inside the waveguide goes to 0. We essentially restrict ourselves to just the one cavity and the one atom that's attached to it. This essentially becomes the space of our bound state. A single cavity plus an atom, this is the James-Cummings model. This is something that we analytically understand. This is something we can solve. And so basically this is an exact a limit that we can solve completely, where we know the eigenstates, where we know the eigenenergies, and then we can say, okay, we know there's going to be some transition between an n photon and n-1 photon bound state. In this James-Cummings limit, this essentially boils down to saying, okay, my n photon James-Cummings state has to have the same energy as my n-1 James-Cummings energy. This energy is dependent on, where I have it? Yes, on my coupling G, on my repulsive interaction U. So I'm going to find some kind of ratio between my G and U, where this energy is going to be the same as this energy, plus some energy on being a cavity. And so this condition here essentially then shows me, okay, in this limit, that's exactly when I have my crossovers. And this is what we essentially sketch over here. On one hand, sweeping this ratio of G over U. Here we also plot kind of for completeness also the detuning. The detuning is the energy difference between sitting in a cavity and sitting in an atom. In general, the detuning is something that, here we kind of discuss it a bit or show it. Later on, we just set the detuning to 0, simply because it's another parameter and from sort of our analysis, it doesn't really add that much new physics. That's why kind of like, just for simplicity, we set it to 0. But what we see here is that as we change this detuning and this G over U, we get different regions in our phase space where the lowest eigenstate is either going to be the single photon, like only one photon is bounded, 2 photons are bounded, 3 photons are bounded, 4, and so on. And so just from this kind of simple Jaynes-Cummings picture, we can already kind of distinguish between different parts of the phase space or different ratios of GU where these different bound states occur. And we can also kind of have an analytical expression for these, for where the transitions occur, with the caveat, of course, that these lines are only valid in this Jaynes-Cummings limit, because this is a simple kind of analysis, or like simple picture that we can look at.
For the first excitation, I guess there's no interaction.
Yes, yeah.
But for example, for n equals 2, can you tell me like
I mean, okay. I mean, if you have, so in general, if you have, okay, the other way, if you have no interactions, then your energy is just a Jaynes-Cummings energy, or you can have a single bound state. Then if you have no interactions, your lowest bound state will always be with as many photons in there. In general, like it scales as G times square root n, the energy. So square root of the number of photons in there. So if I don't have any repulsive interaction, my lowest energy state will be as many photons bounded as possible. And so this will always be the case. Detuning can change this a bit, but that's why we kind of set this to 0, so we don't have to kind of like deal with that kind of degree. And so that's why kind of adding now this interaction, that's why also like the detuning effectively for the Jaynes-Cummings is like the repulsive has the same effect as detuning. In general, the repulsive interaction now kind of exactly pushes this ordering around. That we say it's not anymore the n photon bound state, but then the n minus 1, the n minus 2, and minus 3 that become the lowest state. And so this sort of allows these crossovers to happen. Without interactions, it's just n photons is the ground state. Does that make sense? Okay, great. Good. Okay, so now that we kind of get a picture of saying, okay, we can understand these transitions, we kind of know where they come from, but we only really have it sort of exact in this kind of perfect limit where J is to 0, and we're essentially not looking at waveguides, we're just back at cavity QED, right? But we want to do waveguide QED, we want to see this sort of dress, this exponential kind of like size of the bound state. So in general, you can, expand this a little. Say, okay, let's kind of like start with some numerics first. Here where we show is essentially, we can look at the average occupation of the cavity that is coupled, where the atom is coupled to. So sort of like the central cavity here. We look at the average number of photons there. And here in these simulations, we start with a system of 4 photons. We see all 4 photons are coupled. And as I now increase my repulsive interaction, what happens is I see sort of this level crossing transition of less and less photons are bounded. The way I sort of like to picture this is that you say, okay, initially all photons are bounded. What happens now is that I increase my repulsion. Photons don't like to sit close to each other anymore. And eventually you have this transition point where one of the photons gets emitted into the waveguide and the other n-1 photons get again like localized. So this gives you then like a transition. And so in the Jaynes-Cummings limit, if you have just a cavity in the atom, this transition would really be step functions. It would be sort of like perfect points where this transition occurs. If you, however, have a finite hopping, so if there's a finite size of your bound state, as we see here, these transitions become blurred out, like it becomes like a smeared out kind of like range in the parameter space where these transitions occur. The way you can kind of picture this is saying, okay, initially, so the bound state is not going to instantly emit a photon. It will first start sort of to expand its size, that it will start to kind of increase the average spacing between photons. This already kind of reduces the energy penalty of the repulsive interactions, and only after some kind of critical point then you actually have this emission. So this essentially kind of leads to the smearing out that we observe here. Yes, like one way to kind of like study this is that we looked here is an effect, creating an effective model where you can say, okay, we can essentially reduce this transition into a single body, basically into a single body Hamiltonian by saying, okay, you can project this sort of geometric impurity into an on-site impurity with kind of like two modified coupling, hopping strings. Yeah, essentially what this looks like is you can define yourself a state which is a polariton, also like a kind of like a bound state on your side n, and any other state is then this bound state minus one photon, and the one photon is free. So you just look at the transition of n photons are bounded to n minus one are bound, and one is somehow free. If you just kind of like project yourself into this transition, you can essentially calculate matrix elements for the hoppings, and you can get an effective single particle hopping or a single particle Hamiltonian, where we just essentially analyze this single photon. Does it want to kind of be bounded to this on-site impurity, or does it want to be free? So you kind of reduce it like that. This is then what we show here in color. These transitions that we observe in this effective Hamiltonian. The black crosses, this is exact diagonalization for the full system. And we see these colored lines are then predictions that we get from this effective Hamiltonian.
This book, we see that the population in that specific site is but probably a stupid question, but how do you know that that photon is like unbounded? Maybe it's bounded somewhere else.
I mean, okay, so the measure itself, for like just looking at sort of the central cavity, is not perfect, but because I mean there is this exponential dress that you have to consider. I mean, you can be sure it's not bounded anywhere else, because right now we're only looking at basically an infinitely large waveguide, but only one atom. So the only states that you can have is it's either bounded or it's free. Yes, exactly. So like this is a little bit this picture of saying it starts to expand. Like this is this kind of idea that you say, okay, there is some sort of expansion, right? The photons will start to delocalize a little bit, still being bounded. And only after like a while you actually get like something where you can say, okay, I only have three left, and like I don't know, one is gone. Yes, but it's exactly the sort of like this muddier kind of transition where it's not super clear, okay, like how localized are they anymore? You can just exactly, yes, it's exactly this, like that your transitions are smoother and smoother. And I shown here in these gray lines, this is exactly what the James Cummings would do. So the gray line, this is exactly in the perfect J going to zero world. This would be just a straight line. But because you now have this finite hopping, and because they can basically avoid each other by expanding a bit more, you get this smeared out transitions, which just, becomes like an effect that you have to consider. Right, exactly, like and these lines here are for the James Cummings. Yes, so basically now we understood, okay, in the James Cummings, we have sort of a very nice analytics expression for where exactly these things are. We also say, okay, we have some understanding, okay, what happens in these smeared out regions. But like what can we do from that? So one thing that, so now that we understand kind of like how single bound states kind of behave under these transitions, I will be going later on to a many body case. So kind of like to build up a little bit intuition of what's going to happen there.
So anything, so because in the end what you are saying is that when you do have vector having the rest of the houses, so draws these kind of transitions and states of the dynamic. Right? So in a intro of the rest of the country, as if like the country was glossy, you know, because they have these costs.
Okay, I have to say I haven't thought about it in this way. So possibly, but it's not been a thought that like I'm thinking about. So I wouldn't know kind of for certain right now. Yeah. So okay, it's a good idea. Okay, yeah. So now that we understand a little bit single particle or like single bound state transitions, I want to kind of like raise one point about many particle transitions. So here, essentially, now we're looking at a system where you have two bound states, or like two atoms. Each of them has some number of bound states. For the simulations here, I put 2 photons per each atom. And so once kind of like, okay, if our coupling G is large enough or our repulsion small enough, we know each of these atoms is going to have 2 photons bounded to it. They're going to be localized each there. And this is what we show here with some density-density correlations, where we calculate the correlation between a photon sitting right in the center between the two, and then kind of the second one is like spatially distributed. We see, okay, essentially both of these photons are like, both of them are like localized around each of the atoms. Now what happens is, as we now increase our repulsion, exactly this picture happens of the bound states start to expand, and like they kind of like start to increase the dress they have. This can happen up to a point where they start to overlap, right? And then the question is, okay, once they start overlapping, it's not so well defined anymore to say you have a single bound state anymore, right? I mean, if you have now sort of like a larger function that is hybridizing, so you get like some hybridized states. Hybridized states in general have been already analyzed, but usually I think like for a few body cases. If we scale this up to very large system sizes, like kind of periodically, these become very large hybrid structures. Effectively, though, what we see is we know that kind of like shortly after this, as we increase this more, we're going to have the emission of like some photons, right? Like sort of this is what the bound states want to do. If we now look at our correlations, what's interesting is that we find exactly at these like critical points, right at the transition, we find that effectively the charges, the correlations between these charges are, okay, essentially it's the correlation profile is that of hardcore bosons that we observe here. Like it's a sort of sinusoidal curve. Essentially what this means is that the photons that essentially want to become delocalized start screening the contributions that we see from these atoms. And that we essentially just, that these single photons essentially see a bath of just hardcore bosons, of kind of like other hardcore particles, but like freely, essentially kind of like in the system. Which is going to be something that we'll be touching on later on as well. But then once the transition occurs, right, and so you get this critical point, the photons are emitted, each bound state now sort of like a smaller bound state, again, localized around its atom. So far, we just kind of talked about, okay, the photons that are kind of like emitted, they're now free in the waveguide. But this is only fair as long as the waveguide is just kind of like one big continuous chain. Now the picture is that once this photon is emitted, it can travel along the waveguide, but then it hits another atom. And the photons, and around this atom, there are still photons. And if a repulsion is very strong, these photons here will essentially project a very strong potential barrier. So now what we have is this atom that was emitted here, essentially is trapped between two large potential barriers, resulting from the still bound photons. And they're, in case, so they are delocal, or like they're unbounded from the atom, but they're not free. They're still localized. Now just localized kind of in between these two potential, in this potential well, rather than localized around the atom. And this is going to be, yeah, this is something that we show here, where if you look at your correlations, you see, okay, if one particle sits kind of like in between these two atoms, there's no other particle sitting here, and the next ones can only sit in the next potential well. So that means also that we have really a uniform kind of distribution of our photons. Like you cannot have two photons sitting in one well and then zero photons sitting in the next well, but you always have kind of like a smooth, homogeneous distribution of one photon, one photon, one photon, and at the next transition you'll have two photons, two photons, two photons, and so on. It's going to be a smooth, but yeah, it's a homogeneous distribution of these photons. But this also means that unlike at the transition, where you have hardcore particles that are essentially kind of moving as far as they want, right, like the long-range correlations, here again, these photons are localized, these photons are localized. You again have trapped charge carriers and nothing that could lead to any sort of like long-range correlations or mediate any kind of interactions in the long range. Everything is again localized, which is something that will be coming on in a second again. So now that we understand, okay, these transitions, like how they affect kind of like, how this kind of like changes also with the many-body case, I want to touch on one kind of thing that's really like well-known in the literature a bit. This is the Jaynes-Cummings-Hubbard model. This is sort of the simplest way to kind of generalize this waveguide system by saying, okay, we just look at our chain, and now we just put one atom on each of these cavities, right? So we leave no space in between. Each atom or each cavity has one atom in it. And so what we want to say, okay, then now we can do, we basically assume infinitely large system sizes. Numerically, this just means very, very large, that boundary effects essentially become negligible. And we consider a system where we have two particles, right, per unit cell, which means for each cavity atom pair, we initiate our system with two particles. What's interesting there is then we essentially see an interesting phase space occurring. On one hand, if our J hopping, so our hopping in the waveguide is very, very large, which is close to the origin, essentially these atoms don't play much of a role. The hopping is basically all the photons want to do. It means we have essentially, or effective Hamiltonian just becomes just a waveguide. So it's just the hopping inside the cavities. All the photons become completely delocalized, and all of them essentially kind of condensate to the lowest K mode. It's just a state of completely free photons inside the waveguide, which is just a superfluid. Now, if we increase our coupling G, like so our coupling between cavities and atoms, what happens is photons will want to start to localize around here. And they will do this on each of these, in each unit cell. And what happens is that after some point, you land in an insulating case. This is already well known. This is actually one of the major reasons why people have studied these James-Cummings Hubbard models. It's a way to essentially simulate repulsive sort of interactions, like in a sense, and exactly kind of observe this transition between a superfluid and an insulating phase. Because now you say, okay, 2 photons are localized here, 2 photons are localized here, 2 over here. If 1 photon were to hop over here, this would be a huge energy penalty because my energy scales is G times square root n. And so if my G is very large, I would have to like pay a huge energy penalty to hop to the next neighbor cell. So essentially this kind of huge energy penalty, this is exactly the physics of Mott insulators, right? Like hopping to the nearest neighbor cell costs me a lot of energy. That's why I don't do it. Everybody stays basically on their side. So this is a way to kind of drive into a Mott insulating phase. On the other hand, if we now add increase our interaction, our photon-photon interaction, the waveguide, that means photons don't want to occupy the same cavity anymore. So each of them wants to sit on their own. Because you have 2 particles, one of them will escape into the atom. And you land essentially with a state where 1 photon is completely localized in the atom and 1 photon is in the cavity. And this again for each of the unit cells. Driving essentially also into a Mott insulator. This, so basically driving with a repulsive interaction on site. This is the orthodox standard Bose-Hubbard way to do it. I think this is just our interaction is exactly the Bose-Hubbard interaction. But so basically, I would say basically both transitions in themselves have been known in some way in some of the literature. From what I know, no one has kind of combined this in this sense. And what we see is again like this sort of basically like like a more complex Hilbert space, a more complex parameter space, where we also see this kind of transition now between the 2 types of Mott insulators, because that's also a different point. If you have just a filling of 1 particle per unit cell, then all of this would be just the same Mott insulator. This is just the Mott insulator, but it's the same type of photon sits here plus photon sits here. It's only when you have more than 1 particle per unit cell, so minimally 2 particles, that you see actually that driving, like basically either G or U can drive into the Mott insulating phase, but it's going to be 2 different types of insulators. Either we have a sort of like a stationary state, where both photons, like where each photon is stationarily over here or here, or we have this G-driven case where you still have this kind of like internal fluctuations. So like particles are still allowed to hop between cavity and atom, but they're not allowed to hop essentially to the next neighboring unit cell. So essentially, what we find is all of it drives into a Mott insulator, but we find these are different Mott insulators that kind of like we drive into, and that there are transitions. Let's see. Okay, so now that we understand this picture of the James-Cummings Hubbard, we can say, okay, the last kind of generalization we want to do is one where we say, okay, instead of looking at 1 atom per cavity, let's make space between the atoms. So now we have several cavities that have no atom coupled to it, and only every nth cavity has an atom to it. What happens then? Something I would say kind of like very interesting happens. We get a much more complex phase space. Right? So instead of just a simple superfluid and some insulators, what we observe now is several insulators, actually. So plotted here is, again, like for very large system sizes, I'm looking at, again, the occupation of this coupled cavity. But instead of just looking at the occupation, I look at the variance of it, which gives me something like a fluctuation. So I'm measuring essentially, okay, these particles here, are they all basically uniformly the same, or is my ground state kind of like, does it have fluctuations in it? Fluctuations, for example, I would expect if I'm in a superfluid, because then locally my states are a coherent state, so my variance is going to be very large. This is something that I observe in this region here, and in fact, exactly as my J, so my waveguide hopping, right? Like when I know I'm in the superfluid. This is exactly what I observe here in this bright region, that my variance is very large, and I'm in a kind of perfect superfluid again, where all photons condensate to the lowest K mode and are essentially Bloch modes. But over here, what I see is I see essentially a variance that goes to 0, which means I'm in an insulating state. All the photons are essentially rigid and localized around there. And what I can find here is essentially what looks like lobes of insulators. And okay, I use the word lobes because it is very reminiscent of the Bose-Hubbard model, where you have also Mott lobes that have, let's say, qualitatively exactly this picture. These are regions of insulators separated by some kind of conducting phases between them. And each of these lobes you can label with a particle number. For the Bose-Hubbard model, this is the average number of particles that sit on a side. So for the Bose-Hubbard, it's 1 particle sits on a side, 2 particles, 3, and so on, in each of these lobes. For us, this labeling is the average number of photons that are bounded to my atom. So the number of bounds, number of photons that are participating in the bound state that we've discussed. This is how we can label these Mott lobes. These Mott lobes. Now, what's interesting is, and that's a little bit the unique part here, for the Bose-Hubbard model, the y-axis is a chemical potential. Right, like this picture that you get for Mott lobes separated by a superfluid phase for the Bose-Hubbard model is done doing mean field treatment, which explicitly means you add a new term where you get a chemical potential, which means you treat your system in a grand canonical ensemble, and you allow explicitly for particle fluctuations with some bath and your system. And then you say, okay, given a certain chemical potential, I will have X amount of particles in my system. We don't have that. We don't have a chemical potential in our system. Like I said in the beginning, our Hamiltonian is completely charge conserving. What happens here instead is that we initialize our system with a certain filling factor, a certain number of photons, kind of per unit cell. This filling factor will also then kind of dictate the largest Mott lobe that I can have. For these simulations, this was 4 photons per unit cell to kind of still keep it numerically manageable. And then what happens is, instead of kind of giving my particles to some grand canonical bath, what I observe here instead is that initially, right, if my coupling is very strong, all 4 photons are bound. Like this is what we said initially. If my coupling is strong, the ground state will be everybody's bounded to my atom. But as I now increase my repulsion, so this ratio goes down, this is exactly when I observe my transitions occurring. This is when photons get slowly emitted into the waveguide. The waveguide then means sort of the few cells that are in between. Like this is then sort of like my free parking spaces where I can put the photons that I don't want participating in my bound state anymore. And this is then what kind of transitions me from less and less photons participating in my bound states. And so, yeah, sort of the nice takeaway from this is that what I sort of like the most about this project is that essentially you observe, or we obtain here a parameter space that is very reminiscent, or like kind of, yeah, qualitatively exactly the same as the Bose-Hubbard, right, which is one of those like fundamental kind of like archetypical systems to study in condensed matter systems. But you can get it essentially without having to do this mean field treatment, without having to go into the grand canonical ensemble, right, which means experimentally, you don't have to somehow engineer yourself some bath that you can do particle couplings with that you allow for these interactions, right, which is a huge sort of like thing you have to kind of consider then. Right, in this setup, you can essentially use as a quantum simulator to study the kind of these transitions and effects of the Bose-Hubbard model, but while kind of like engineering everything kind of like a priori. So you initiate your system, you say, okay, this is my filling factor, and that's it. And then you just let it run isolated from everything else, right? Which is sort of like an advantage you can kind of like engineer with. Yes, exactly. Okay, this is the chemical potential. Yes, okay. Mm-hmm.
How do you actually record
how you
this goes on for a certain distance.
Yes. Mm-hmm.
When this distance goes to 1, 0,
yes.
Yes,
I mean, so like, yeah, if the distance, so basically if you take away the cavities and the distance goes to, 0 or like 1, then you get the James-Cummings Hubbard. Yes.
So the space diagram holds for a certain automatic distance or this kind of
in general, okay, so it holds in general for larger distances. I would say sort of the physics works nicely. This is a little bit like a caveat. The physics works nicely if you have here more cavities than photons in it. Because the problem is like, okay, once I have sort of like 3 photons that I emit and 3 photons are sitting here, then emitting a 4th photon would also cause an energy penalty, right? Which is possible as long as my repulsion is finite. It essentially just means that I kind of like I shift the lobes. Yes, so like, yes. So this picture right here is kind of for more cavities, like for large distances, compared to the number of photons. It still works if I have more photons than cavities. It's just, I'll say like the picture becomes a little bit more complicated and I'll say like a little bit more non-trivial, kind of like where exactly the transitions are, but the physics still is the same. Yes. No. Yes.
Here, like you're talking the limits.
Yes.
So, are there any signatures? Something is in are there any signatures of what you were expected to having before this kind of instructions of focus upwards? Can you see from this that effect or it's something that is
Do you mean if this trapping of photons, is this has some effect here?
Yes.
Yes.
There is some features that you have discussed and say because there are photons stuff.
Yes, exactly. Okay, that's a good point. I should have clarified this better. This trapping is the reason why we have insulators in the first place. What happens is, if I initiate with 4 photons, as I did here, I say, okay, all 4 photons are localized here. Great. That means no photon essentially kind of like moves anywhere. Then obviously I have an insulator because each photon is bounded to an atom. But the moment I have my first transition, I have my 3 photons, right? Like if I have then only 3 photons bounded for each atom, well then the 3 photons I would naively assume would then be charge carriers that could then carry long range interactions that could allow for variance. Here, I mean, I'm just plotting the variance to kind of like have this nice picture, but we've also done studies looking at like single particle correlation functions. And what you really see is that, I mean, here you have long range correlations. I mean, so in the superfluid, it becomes flat. In these transitions, you get 1/square root correlations, which is hardcore particles, right, which kind of like goes back to this hardcore picture that we had in the transition. And in these insulating phases, you really have exponential decay, right? So it's really, there's no charge carrier that can carry anything. And the way to kind of like understand this is exactly what you were mentioning, is because the photons that are emitted are still trapped. They're still localized. So these are not free carriers or like free particles that could carry any charge. They're still trapped. So the photons that are bounded are trapped, and the photons that are emitted are still trapped. And this is why, for these lobes, I still observe insulators.
How these lobes would be just lines.
Yes, exactly. Yes, I mean then yes, I mean like if I would not have this effect and these particles become charge carriers, then like for this picture I would see color here basically. Then like this is not a well-defined insulator anymore. I might still have some change of okay less like so the charges might be slower or less kind of like straight, but yes, I would have some. It wouldn't be an insulator anymore. And so exactly this trapping is exactly the sort of the physical motivation and reason why these states are all insulators, even if photons are sort of emitted away from the bound state.
Very stupid question. So these black regions are something that is
Yes. Yes.
So there is one thing that would surprised me from this plot. So normally going down with the number of the particles in the field, normally what happens is that the dimension of the jitter of this area becomes smaller and smaller. Instead, from your plot, seems to become larger.
Yes. Yes. Okay. So definitely. So like this is, I would say, sort of like when then the caveat comes in of it is the system that we have here is not exactly the Bose-Hubbard model. Right? I mean, there are differences of bound states and kind of like how they behave to the orthodox Bose-Hubbard. What we do see, I mean, okay, maybe this is yeah, maybe not so perfectly seen here, but technically these modes, they do actually, these lobes do decrease in size. I mean, this one is much larger than this one and this one.
Since the energy is modeling
yes.
number of particles, so nobody wants to understand the geometry of the cloud.
That's the graph is an effect E over U and J over U.
Yes.
Typically in this kind of models, right, I don't know, mu over J.
No.
I mean, over U, I mean, like usually it's like G over U here, but then there's like a mu over U. That's fine. So like mu, it does have a slightly different thing. This sort of the change here, right? This also is, yeah, basically, okay, this is also a bit of an effect of this finite particle effect that, yeah, sort of if we only initiate our system with 4 photons, it means up here, like there cannot be a 5 photon lobe. So what happens is that this mod lobe essentially starts expanding and becomes very large, right? But this is only because we only initiated 4 photons per particle, per unit cell. If we had initiated with more particles, then this would also be more and more lobes that also become kind of like narrower on the y-axis. Yes, good thing. Yeah, okay, so with this, yeah, I'm actually happy to conclude. So essentially, yeah, we studied a waveguide QED setups. Sort of the addition that we kind of like tried to specifically look into was adding these current nonlinearities, right, that we motivated from the circuit setups where it's very easy and very natural to kind of like play around with the circuit elements, and add this interaction basically inside the waveguide, which, okay, like for us, we term it sort of photon-photon interactions. We've investigated sort of like how this changes. We see, okay, these bound states, there are these kind of changes of the ground state that we observe. And yeah, lastly, we essentially get a Bose-Hubbard type phase space, right, which is nice because it kind of, you don't have this chemical potential, which you usually have to deal with in these type of settings. Yeah, the work is on archive, and with that, I'd like to thank my supervisor, Peter Rabel, and my collaborator, Jacques Landonneau, and I'm happy to answer any more questions you have.
Any more questions? I have one, just as what happens, or if you have any idea what happens, if the hopping rates are like
That's a good question. Yeah, Enrico asked the same question the other day when we discussed it. It's something I haven't explored. I don't know. It would get more complicated, yeah. And yeah, this would be exactly, I mean, probably a whole additional project you can do with this. Yes. Yeah, so far, yes, yeah.
If you do the other two within a month, probably you're up. Because here you do the other two in the month, right?
Yeah, I mean, yeah, the detuning is just 0. Yeah.
So probably.
Yes, so I think in general, the detuning, it has sort of like a similar effect to what the photon-photon repulsion has. But I would say like there's sort of like a limit because you can only kind of like detune. I mean, if you kind of like make a atom kind of like below your band, that means just, okay, one particle will always sit there. You sort of like, you're more limited in kind of like what you can do. So you cannot like get the, like you couldn't just with the detuning kind of like get this sort of like larger complex phase space. But I would say like if you start kind of like playing around with the detuning, you'd be modifying this parameter space. But I think sort of there's not going to be that much different physics happening. You'll just be like changing, I think, sort of where the transitions are occurring. This is my understanding at least of it, yeah.
Another molecular organization, I already asked you last year, is the 2D lattice per lattice.
You mean extending it to 2 dimensions?
But first of all, if people study that it's coming apart for 2D per lattice.
I don't know from the top of my head the paper that has done James Cummings Hubbard on 2D. Yeah, so like not from that, and also I mean this we haven't come to the. I mean. What do you mean? I mean this like this trapping physics. Yes. 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 Yes, exactly. I mean, then the question is, okay, if you take away sort of the middle cavities, then you could still engineer it in a sense that if you have larger squares. Yes. But yeah, you would have to engineer it or like kind of like then define it in a very specific way to have it. But yes, yes. Yes. But yeah, good point, yes. Yeah. That's why I guess like yeah, you can engineer yourself a 2D system where this sort of still works then. But yeah, it's not trivial. Yeah. Yes, this is all 1D. What do you mean? Yes. That's a good point, yes. So far I haven't really thought that much about like 2D implementations, but yeah, that's a good point. Yeah, but, yes. Yeah. But it's a good point. I mean, I guess, yeah, like you could think it's probably wouldn't be so hard to think of ways to engineer it into 2D, yeah. Yeah, so far, yeah.
Let's thank the speaker again.